that this sign is going to be positive, right? And it also means that when we reform the bonds on the other side, we are going to get energy out, right? So its sign is going to be negative, right? So if we add these two together, essentially, to figure out the energy change, we would see that this is going to be a negative, that's going to be a positive, so we should end up getting a negative energy out. This should be an exothermic reaction. And it's exothermic by I did my math right, 55 kilojoules, right? So we are adding those two together because the products are going to have a negative, or we can talk about the delta H of this reaction as being the sum of the bonds broken minus the sum of the bonds formed. Right? Which, if you're paying attention, is exactly the opposite of the way we did it last semester. Right? Last semester, we took delta H of reactions as products minus reactants when we're talking about heats of formations. Now we're doing something different because we're talking about adding energy or taking or getting energy out. So the reaction itself or the equation changes. Right? That makes sense. All right. Questions on how to do those calculations? I want to take a closer look at this bond right here, right? So that is a double bond. So if we look at it down here, and I'm going to also rotate it so it makes more sense to me, right? We're going to have this carbon, and it's going to be double bonded to the oxygen, right? And then off of this carbon, we're going to have two other groups, which I'm going to call R1 and R2, right? We don't care what those are. We can look them up. They're up on top, right? They're both other carbons, and actually R1 and R2 in this case are the same, but it doesn't matter, right? Is everybody okay with that? We're focusing on this carbon right here. Right? So we can talk about the types of bonding that's going on there. This single bond here is the direct overlap of, and we have energy between the two, or the electrons are existing between the two nuclei, right? And we call that a sigma bond. If we look at the carbon here, and we'll come back to this terminology, a single bond has electrons between the two nuclei and then above and before. So one of these arrows, or one of these bonds, is the sigma bond. And the other is what we refer to as a pi bond. And we'll come back to this example again later when we talk more about this bonding. But if we look at what's going on here, the single bond is going to be sharing 2 electrons. The double bond is going to be sharing 4. Right? A triple bond then would be sharing 6. That makes sense? All right. And we also talked about we introduced this idea of unequal sharing, right? So we can talk about how, that's correct. Am I getting ahead of myself? Did we talk about electronegativity in this lecture? Yeah, okay. And we talked about polar covalent versus ionic. Okay. So we can think about this sharing of electrons as a continuum. Right? On this end, where everybody shares well together, we call that a pure, actually not try to write with highlighter. Pure covalent. Jeez. Covalent. right? Which means that everybody shares, not one atom is spending more time with the electrons, right? It's what we hope, right? This is what adults are supposed to do. If we look at the other side, right, where now we're no longer sharing at all, right? One of the atoms is actually stealing that electron, and when we transfer the electron, we call that type of bond what? Somebody? This is the ionic. Right? This huge region in between covalent, pure covalent, and ionic is referred to as polar covalent. Right? And that's based on the difference in electronegativities between those two atoms. Right? So if we look up here in this example, right, which is oxygen or carbon more electronegative? Somebody in the virtual world. Which one is more electronegative, carbon or oxygen?
Oxygen?
Oxygen. Yep. So if we look at our periodic table again, right, electronegativity, that's a horrible periodic table, but we're going to get over it, does the same thing as all our other trends except for atomic radii and increases as we go up. And now our friend up here, fluorine, is the most electronegative. Typically, we ignore the noble gases because they're noble and they don't interact with us, right? So that means that the oxygen is going to share electrons or want electrons more, right? So we are going to see color, can you guys go with lime green? We're going to see that the electrons in this shared bond are going to be pulled toward the oxygen, right? Which is going to leave the carbon feeling lonely and upset, and he's, well, opposite, he's going to become positive, right? Which sort of is not true. Right? Somebody's not sharing with you, you don't become positive, but in this case you do, right? So we can see this difference in electronegativity as represented by this arrow within what we call the Lewis structure, which we'll talk more about next time. But I refer to this arrow in the activity for today, right? And this bond here is going to fall in the middle, sort of the middle of this continuum, and be referred to as a polar covalent bond. And we have distinctions where these transition occurs based on the actual difference in electronegativities, right? So from the lecture, what was the sort of cutoffs between pure covalent and polar covalent? It was a difference in electronegativity of what? 0.4, right? Everything on less than 0.4 we consider pure covalent. Everything above 0.4 we consider polar covalent until it gets to this limit over here, which was at a value of what? 1.7. Right? So if it has a difference in electronegativity greater than 1.7, we're going to call that ionic, right? And if we look, for example, at, say, chlorine and sodium, if we looked at their difference in electronegativities, we find that it's something like 2, right? Which means that sodium chloride is going to fall over here as an ionic compound, as we've told you, right? Typically, unless you're looking at the values, the only way is they have to be very close to each other on the periodic table for them to fall into this pure covalent compound, right? And typically, the only case at the time that's going to occur is when we have something bound to itself. So up here, this one is going to be pure covalent. Actually, the difference between carbon and hydrogen is also less, it's like 0.4, I think. So it's also going to be considered as a pure covalent compound or bond. Does that make sense? Questions on any of that? From anybody out there who's not sitting in front of me shaking their head? Okay. The last thing I want to say is I'm trying to make for your in-class, well, all of the activities, I'm trying to reduce the uncertainty about how to enter things in, right? I tried it on the integrated problems and you guys completely ignored me. Right? I said, I want you to enter it, not everybody, but a lot of people. Let me actually stop sharing. So I tried to have it, now I gotta remember which camera's on. I tried to have it so that the way I wanted stuff entered would be clear on the activity. So for today's activity, I've asked you to enter stuff with a less than or greater than sign, right? Because I am old and I had to actually take typing in school, I always separate stuff with a comma. So when you're asked to put something in with a greater than or less than sign, put the formula of the first one in, a space, then the formula, the less than or greater than, whichever is important, and then a space, because that's the way I type naturally. Right? I have to actually physically stop myself because I actually, did anybody else have to take typing when they were in school? I physically, and I typed on a typewriter. So you can imagine how old I am, right? I had a classroom full of typewriters where we typed and learned to type on. So, okay. Does that make sense? Questions about anything? There are several questions in here where they're sort of open-ended in this activity, asking about how bonds are shared. They're fairly straightforward, so you shouldn't have any ambiguity on your answer, but how you answer them will be slightly different. So I'll have to go in and manually grade those. But in more cases, I'm trying to be very specific about the things I want. Also, if you're asked to do a calculation, all I want is the number and then a unit. You don't have to put any descriptors on that. So if you calculate like a theoretical yield in grams, you would put the number and then grams, and then you would stop writing and use the unit. Does that make sense? Questions, comments? All right. If there's nothing else, let's break into our groups and get started on today's in-class activity.